Hey guys, Mr. Gucci here, and I'm just going to walk through the 2.2 notes, which is uncertainty. All right. So, one of the things that we talked about earlier in this unit is the idea that it's important in science to be as correct as you possibly can, as exact as you possibly can in your observations. And that means acknowledging sometimes when your observations are incorrect or somehow relaying to people how sure or unsure you are of your results. So understanding and being able to communicate uncertainty is incredibly important in science. So first, just a couple basic terms. The first term is accuracy. Accuracy is just a description for how close someone is to the true value of a measurement. So, for example, this coin right here is made out of aluminum, which has a density of 2.7 grams per milliliter, or grams per cubic centimeter. All right? Accuracy would be a question of, if you took the density of this coin, how close do you get to 2.7? Accuracy is how close your measurements, your observations are to a true value. Now, on the other hand, we have a concept called precision, which, while often mistaken for accuracy, is different. Precision is about how consistent your results are. For example, when you take the density of these aluminum coins or other pieces of aluminum, can you consistently get a density of around 2.7? All right? If you can consistently get the same results time and time again, that's called precision. Okay? It's possible to be one and not the other. For example, maybe you're taking the density of aluminum, and every time you do it, you end up with a value like 0.5, all right? Which is way off of the actual density. But if you're taking the density of different aluminum samples all around your house and you keep getting a density of 0.5, then you are precise. You are somehow doing the same thing every single time, even though you are wrong. Okay, here it is communicated with pictures. Okay, here's a picture of someone who's accurate and precise. All right, they're hitting the bullseye and they're clustering their shots. Here's someone who is not accurate because they're not near the bullseye, but they're still precise. They are continuing to cluster their shots. Okay, this is accurate but imprecise, okay? Accurate but imprecise. They're accurate because they're close to the bullseye, but they're imprecise because they're not clustered together. They're spread out. And then this poor sap right here is neither accurate nor precise, okay? Accuracy is about how close you are to the true value. It's about hitting the bullseye. And precision is about, can you cluster your results together? How close can you get, okay? So we did some sample problems in class where kids tried to demo this, all right? Cool. Now, here's a question. All right, two people. All right, we got Logan Paul and Aaliyah. They're shooting at a target range. Okay, Paul is more precise, while Aaliyah is more accurate. Who would you rather have on your team in a paintball match? Okay, who would you think would have a better shot at becoming more accurate and more precise? And we talked about this in class, and the answer is Paul. Paul actually has the potential to be the better shot more quickly here. And the reason is his shots are clumped together. Okay? All he needs to do is to calibrate, okay? He's aiming up and to the right. If he just points his gun down and to the left, then every time he shoots, he's going to get it on bullseye time and time and time again. Aaliyah would have a harder time because she's near the bullseye, okay? She's just all over the place. She's going to have to work harder to focus her shots in more closely, okay? So here it is in a scientific environment. Again, Paul and Aaliyah went off to the lab to calculate the density of aluminum metal. After many tests, their results are recorded below. The actual density of aluminum is 2.7 grams per cubic centimeter. Now, based on this, Paul is more accurate because he consistently gets results that are closer to 2.7. But Aaliyah is more precise because her answers are consistently getting around the same value. I mean, look at Paul. His answers are plus or minus half a gram per cubic centimeter, whereas Aaliyah is only off by 1/10 of a gram per cubic centimeter. So her results are more clustered together. And if I had to choose who I'd have as my lab partner in this activity, I would choose Aaliyah. I would choose Aaliyah because even though her answers are farther off the mark, clearly she has some kind of procedure down and is extremely regular in her results. If we can just figure out what's throwing her results off, maybe it's a misaligned scale or using the wrong units in a graduated cylinder, as soon as we solve that problem, she is almost certainly going to be nailing the exact answer time and time and time again. So in science, if you had to choose, I'd rather be more precise than accurate because I can just adjust my results to get myself back on target, okay? Now, those were all qualitative descriptions of accuracy. It's just saying, oh, you're accurate, you're inaccurate, okay? But like I've discussed before, whenever possible, we would like to have quantitative observations. And just like certain observations have numerical versions, so, oh, you're fast, well, how about you say you're going 65 miles an hour? Be quantitative. There is a quantitative way to describe accuracy. So here's a scenario, okay? I think this would be a cool contest. All right, there's a contest where people have to guess the distance between their house and some location far away in kilometers. And the person who guesses closest, all right, they win a trip to that location, okay? And you are the judge of this competition. So the first entrant? First person who signs up is Aaliyah, and she decides she's going to guess the distance between her house and Disney World. And she guesses that it's 1,600 kilometers. The actual distance is 1,620 kilometers. So she was off by 20. Okay? On the other hand, Logan Paul was less confident in his guessing ability. So he decided he would only estimate the distance between his house and the closest Wawa. He guessed 6 kilometers, but the actual answer was 4 kilometers. He should have known better. I've never lived farther than 3 miles away from any Wawa anytime I've been in this state. Okay? Now, Aaliyah was off by 20. Paul was off by only 2. But who would you say, if you had to judge, is the better guesser in this competition? The answer is actually Aaliyah. All right? Even though she's off by more, the number she was guessing around was a much bigger number. She was trying to hit somewhere around 1620, and so that's a much bigger range to guess. So if she's off by 20, only 20. That's much more impressive. All right. Yes, Paul was off by only 2 kilometers, but we're talking about the distance between your house and the Wawa. You should know this already. You should have this memorized. Okay. And it's not that big of a distance. Okay. Look at it this way. You're used to taking tests and quizzes and getting graded on them. If someone comes up to you and says, I lost 5 points on a quiz, and someone else says, oh, I lost 20 points on a quiz. All right. You actually don't know who did better on the quiz, all right? The person who lost 2 or 5 points, well, what if that quiz was only worth, 10 points? Or in this Mr. Paul's case, right? He said, oh, I only was off by 2 on a quiz. Well, Mr. Paul, the quiz was only worth 4 points, so that's not so good. Whereas Aaliyah's like, I was off by 20 points on my assessment. No, what assessment was that? The SAT, graded out of 1,600. If you only are off by 20 points on an SAT, you've done phenomenally. All right, because you need to know what is the range that you're guessing in. And so the way that we quantitatively measure accuracy is called percent error. Okay, it's a quantitative measure of accuracy. It's never negative. All right, just like you would say, oh, I lost 10 percentage points on a quiz. You would never say, I lost negative 10% on a quiz. It's always positive. The percent error is always positive, never negative. Okay? And what you're doing is you're comparing your results, all right, your testing, your guess, your measurements, your estimate, you're comparing yours versus what we know to be the true value, all right, what's been accepted, what's been extensively tested and proven, okay? And so here's the formula. The formula is take the true value and subtract what you got, okay? That tells you how far off you were from the correct answer. Then divide it by the true value. Divide it by the correct value so that we know roughly how well you did compared to what the actual answer was. You have to always compare. Just like on a test. I'm never going to put on top of your test like, oh, -6. What do you say if you see -6? You say, Mr. Gucci, what's my percent? Well, what I do is then I just divide it by the point value of the test, and that's how you know what your percent is, okay? And then you multiply it by 100 to turn it into a percent. By the way, these vertical lines here, these are absolute value lines, okay? Absolute value lines, which tell us, again, that we can never get a negative answer. So I'm going to do 2 sample problems for you to show you how this works, okay? So here we go. We have Mr. Logan Paul, okay? Let's calculate his percent error here. Now I'm going to switch to another sheet, okay? Going to control, highlight everything, delete. All right. let's take a look at this and see how it goes. Okay, so the formula for percent error is true, the true value, minus the guess, the estimate, the measurement. All right, we'll just go with what the measurement is. All right, divided by the true value. And we have to put that in absolute values because it can never be negative. And then we have to multiply it by 100 to turn it into a percent. Okay, so this is the formula for percent error. Now, the true distance between Logan Paul's house and the Wawa is 4 kilometers. He guessed his estimate was 6. Okay, and so we're going to do 4 minus 6 on top, and we're going to, again, divide by the true value, which is 4. All right, now again, all this is an absolute value. It can't be negative. So let's take a look. 4 minus 6 is negative 2. Okay, but again, you're not allowed to have a negative in this, so it's just 2. And the bottom is 4. Okay, so 2 divided by 4 is 0.5. And 0.5 is equal to 50%. Okay, now you can either multiply your decimal by 100, or you can do what I prefer to do. I just bounce the decimal over twice, all right, and turn that into a percent. Whatever works for you is fine. So Mr. Paul's percent error here is 50%. He got it 0.5 correct, and that's 50%. All right, let's try another sample problem here. Okay, let's try another sample problem here, which is Aaliyah. Let's see what her percent error is in this problem. So once again, same formula, all right? Percent error equals the true value minus the guess, the estimate, whatever your measurement was. All right, this is kind of like her estimate, so we'll use that word. Divided by the true value, okay? And that's just times 100. I gotta make sure that's an absolute value, all right? We can't have a negative. If you get an answer that's negative and you think you did everything correct, all right, well then what you should do is just make it positive. That'll probably take care of it. Okay, so the true value here, it was actually 1,620 kilometers from her house to Disney World. But she guessed 1,600, all right? So she was off by 20. That's what we're going to get on top, all right? And so we're going to divide that by the correct answer again, 1,620. Okay? Once again, absolute value. It can't be negative. This time, however, we're lucky it's not going to be negative. All right? So her answer, she got 20 over 16 over 1,620, all right, times 100. 20, I'm kind of running out of room here. 20 divided by 1,620 is, this is weird. This is weird. Okay, okay. So the decimal we get here is 0.012345678 9. I swear I did not plan that. That was totally coincidental and weird. I want to look into that. Okay, so that's her decimal. All right, as a percent, okay, multiply it by 100 or bounce that decimal place over twice. All right, sorry, I'm running out of room here. Her answer is 1.23%. 1.23%. Okay, now I run through every single homework problem that is percent error. So if you want to see more examples, just look at my videos where I go through the homework and solve all the homework problems showing my work. Quick advice for you, 2 most common errors with these percent error problems, right? The 2 most common mistakes are people put a negative. It's not a negative. It'll never be a negative. If it is a negative, you just forgot to make it positive, all right? Just make it positive and you're fine. The second mistake is people round their percents too much. If you just rounded this to 1% and left off that 0.23, that's actually quite a bit that you're leaving off, all right? And my homework sheet will mark it as wrong. If you round it too much, it'll mark it as wrong. So if you think you did everything correct, but it's still showing up as wrong, just give me a few more digits to that percent and you'll probably be fine, okay? Check the homework questions to see examples that I did, all right? And have a good day, everyone. Da, 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 da.